I want now to take a look at an example using a min priority queue, and we'll move through this one a little bit quicker, having gone through the max queue in detail. But once again, we're trying to insert elements in a sequence into a heap. And so we begin with the 9, and we add the 9 here, and our tree looks like this. And we normally would try to heap this up, but so we add at the end, and since it was empty, we added in the first element, and we try to heap that element up, but that has no parent, so there's no heaping up, and so we're done. And we now bring in element 11, and we place it in the array, and then our heap looks like this. And so this is a min queue. So we're going to check if 11 is less than or equal to 9. And if it is, we're going to swap it. In this case, 11 is not less than or equal to 9. And so we're done with the heaping up. And we look at the 6 then, and we're going to enqueue that. And we add the 6 to the end. And then that looks like this. Now our heap looks like this, and we have to heap up the 6, and we ask, is the 6 less than or equal to its parent 9? It is in this case, so we'll affect the swap, okay? And so we will swap the 6 and the 9. So the 9 is now here, and the 6 is here. Let's redraw the tree to keep everything clean. There's the 6. Here's the 11, and here's the 9. And we ask ourselves, do we have the structure property? We do. This is both a complete and a full binary tree. Do we have the heap order property? The 6 is both less than or equal to both the 11 and the 9. So this is in fact a min heap or min priority queue. And so let us now then enqueue the 4. So we add it at the end, and we attempt to heap up the 4. The 4 is now here, and we begin by heaping up the 4. Okay, and so I'm going to underline this. This is a 4. We ask, is the 4 less than or equal to the 11? It is, its parent. So we want to swap the 4 and the 11, and that gives us this picture. And now remember, so let's redraw. So the 4 is now here, and the 11 is here, and the 9 is still where it was. So it turns out that the side where the action is not happening is completely unaffected. We're continuing to try to heap up the 4, okay? We will heap up the 4 either until we're at the root, or we no longer violate the heap order property. We ask, is 4 less than or equal to its parent, the 6? It is, so we make this swap, which is the equivalent of doing this. Okay, and now let's redraw the tree. Okay, so here's the 6. Here's the 9, and here's the 11. Okay, so 4, 6, 9, 11, 4, 6, 9, and 11. And we're continuing to try to heap up the 4 until we kick out of the loop. So we either heap up until we've reached the root, which we have in this case, or we no longer violate the heap order property. We're at the root, and so we have restored the heap. And we will now add value 8 to this heap. So we add it at the end. Okay. And that gives us the equivalent of this tree representing our heap. And so we ask, is the 8 less than or equal to its parent as we try to heap up the 8. It is not, and since this is a min heap, the heap up terminates. Okay, and let's now add a 7. Okay, so I'm going to redraw this tree. Let's redraw it so it's clean. Again, I'm going to redraw it down here. It's a 4 with a 6 and a 9 and an 11. Okay, and an 8. And now we're going to add the 7. Okay, so we add the 7 at the end. Okay, and that shows up here in the tree. And we have to heap up the 7. We ask, is the 7 less than or equal to its parent, the 9? It is, so we make the swap. And the swap in the array looks like the 7 and the 9. Okay, and let's redraw. The 11, and here's an 8 here, and the 9 was swapped with the 7, so it is now here, and we're continuing to heap up the 7. We ask, is the 7 less than or equal to its parent, the 4? It is not, so the heap up terminates, and now our array is 4, then 6, then 7, then 11, then 8, then 9. And our tree is 4, then 6, then 7, then 11, then 8, then 9. And finally, we're going to do a DQ. Okay, now to DQ and a min Q, we're going to do the same thing. We're going to remove the root, except in this case, the root is the lowest value. Okay, so remove the root. Okay, so we'll draw these individual pieces. So let me change pen colors for a second. Okay, so what are we going to do? We're going to remove the root, right? That's step 1. We're going to move the thing that's at the end into the root's position. Okay, that is step number 2. And so let me put a 2 here. And so what have we done up here? We have removed the root, and we have taken this 9 and we've added it into the root position. Okay, and then we're going to actually remove the 9 from this position. Okay, so the 9 is now gone. I did 2 steps there at once. The 9 has been moved to the root position. That's step 3. And finally, we're going to heap down the 9, which is now up here, right? Heap it down. That is, that's the fourth step. Okay. So our tree then looks like this. We've got a 9, and we've got a 6, and a 7, and an 11. And an 8. So if we look at our array, 9, 6, 7, 11, 8, 9, 6, 7, 11, and 8, we're heaping down the 9. And so we ask, is the 9 less than or equal to at least one of its children? In this case, it's less than or equal to both. Because this is a min heap, we will swap it with the smaller child. Okay, so we effect a swap that looks like this. Because the 6 is less than or equal to the 9, and we make the swap. So the 6 is now at the root, the 9 is off to its left, the 7 to its right, and the 11 is here, and the 8 is here. Remember, the value that we're heaping down is 9. That was what was at the end when we moved everything up. And so the value here, we're going to ask the question, are one of its children less than or equal to 9? And the 8 is, the 11 is not, so we're going to swap the 8 and the 9. And our table, our heap now looks like 6, then 8, and then 7, and then 11, and then the 9. And we're going to continue to try to heap down the 9, but the 9 is now at a leaf point. And this is a complete binary tree, so we have the structure property. And let's look at every location. 6 is less than 8 and less than or equal to both 8 and 7. 8 is less than or equal to both 11 and 9. And the rest of the nodes have no children. So we have restored our heap order property, and we are once again a heap.